Hello, this is session 22 and we are going to continue with the prime number theorem. So, the prime number theorem 2. Okay, so in the last session we had proven that real zeta function has no zeros over the vertical line real of z equal to 1. Of course, it has a pole at 1, but it has no zeros beyond in that straight line beyond at any other point. Okay, and it's going to play an important role of the for the proof of prime number theorem. Okay, we also had some relation about zeta function and some arithmetic function that will also play an important role. Now we are going to prove, first of all, we are going to show one. There are many equivalent statements of, in fact, of prime number theorem. It is not the only proof. The proof I'm going to develop here. There are different proofs that use some different arithmetical functions. More or less the idea, and most of them are close, are quite similar, but sometimes are a little bit different. And normally they use some equivalences. So the prime number theorem is equivalent to some other result, and they try to prove this other result. Okay. So what I'm going to show is the following. We'll call it a lemma, that the following are equivalent. First of all would be prime number theorem. Okay? And second would be that limit of psi of x over x is equal to 1. Or, stated differently, psi of x is equivalent to x at infinity. So, and in fact, at the end we will show this. We'll try to show this that this limit holds. Okay. So why is this true? We have already seen that psi of x was smaller or equal than pi of x log of x. So psi of x over x is smaller or equal than pi of x log x over x. So we keep in mind this inequality here. So we are going to, in fact, to show that superior and inferior limits of all of these two functions are equal, are the same at the end. So they are equal and equal to 1. So first of all, we keep in mind this inequality here. Let us observe, for instance, that if prime number theorem holds, this limit of this part is equal to 1. So the upper limit, the superior upper limit of this expression must be smaller or equal than 1, for instance. Okay. Now, second, take some number y smaller than x. Take some number y smaller than x, and consider pi of x. Pi of x would be pi of y plus the sum, okay, of 1. The number of primes between y and x, where p is a prime contained, let's say, between between y and x. This is more or equal. This is also quite tricky. Plus the sum of log p over log y, where y of p is smaller or equal than x. Of course, because this is greater than 1. Okay, and this is smaller or equal than pi of y plus 1 over log y times, you have this sum of log x would be smaller or equal than Okay, this number, this sum of log x when p is prime in between y and x is going to be smaller or equal than this sum by the definition, this number by the definition of the function psi as the sum of the Mangold function. Okay, and finally this is smaller or equal than y, pi of y, we are going to bound it by y plus well, these are quite simple inequalities. I always forget inequalities, but these are quite simple. Now we take one precise value of y. We take y as x over log x to the square. It's also, let's say, quite a little bit tricky. So we have pi of x smaller or equal than y is x over log x to the square plus phi of x over log of y is 2 times log log x, yes, minus 2 times log x here. Okay, so pi of x times log x over x is smaller or equal than x than 1 over log x. Okay, plus we have here phi of x over x times log x over log x. Okay, we have these inequalities, and from these inequalities the results follows. Why? Well, let us assume, for instance, the prime number theorem holds, and as I said before, if this tends to 1, we have this function bounded above by something which tends to 1, and you can bound below using this inequality by this term here that tends to 1 minus this term here that tends to 0, quotient this term here that tends to 1. Okay, this term here tends to 1. So, okay, by the sandwich criterion, it tends to phi of x over x tends to 1. And conversely, if you assume that this tends to 1, your prime number theorem statement is bounded below by something that tends to 1. It's bounded above also by something that tends to 1. This tends to 1, this tends to 0, and this tends to 1. So finally we have the result. So prime number theorem is equivalent to the fact that psi of x is equivalent to x. The second lemma would be that psi of x over x is bounded above. Is bounded above. Okay. So again, it's a little bit tricky. So remember that psi of x can be written as the sum of the integral parts of log x over log p times log p, where p is smaller or equal than x. And let us observe the following fact. Assume you have some number p that is contained between n and 2n, like this, greater than n and smaller or equal than 2n for a certain number n. So this number p divides this combinatorial number, because this combinatorial number 2n factorial appears on the numerator, and the prime number p cannot disappear when you do the quotient here, but because it cannot appear among the prime factors of the denominator. Okay, so in fact the product of all prime numbers here, well, and also yes, this product of all prime numbers here, numbers between p and 2n, must divide this number 2n over n, so must be smaller than this number. That is also smaller than 2 to the n. Smaller than 2 to the n. Okay? So the sum of log p, sum of log p when n is between, where p is between n and 2n, must be smaller than 2n log 2. This question. Okay. This sum, if you take the sum of log p up to some of all the logarithm of all prime numbers up to some 2 to the m, let's put 2 to the some power integral power m, we can write this sum as the sum from k equal 1 to m, let's say, of the sum of log p, where p goes between 2k minus 1 and 2k. So we divide the sum we split the sum in several sums. Okay. So by previous bounds, this term here is bounded by 2k log 2. Is bounded by 2k log 2. Bounded above. So the sum here is bounded by 2 to the m log 2, m plus 1, sorry, log 2. So the sum of the logarithm of all prime numbers smaller than 2 to the m is bounded by 2 to the m plus 1 log 2. This product, the sum of all the logarithms. Okay. Let us also have a look to this sum here. Well, in this sum, the first term is the integral part of some number, but this integral part, in fact, is almost always equal to 1. It can be only it can be, let's say, greater than 1. I mean, at least 2 when p is too small. When p is smaller than the square root of x. In fact, if p is greater than the square root of x, this number is 1. In fact. So we could consider, we could split this sum, in fact. So on one hand, we have the sum, for instance, of splitting this sum, we could have the sum of these terms, the terms where p is smaller or equal than the square root of x, contribute to that sum as and this number is smaller than pi over pi of square root of x times log x. So this is a part of these terms there, okay? And the rest, so finally you have that psi of x is smaller or equal than these terms here, this first part of the terms here, pi of x, pi of the square root of x log x, plus the rest of the terms sum from p, let's say, sum of log p, all the terms would be, in this case, all let's say the integral part would be equal to 1. So I write sum of log p, and I'm going to write here p smaller or equal than 2 to the m plus 1, where we take m big enough such that x is we take some m satisfying these bounds, okay? So we have this sum here, and this is smaller or equal than pi of plus by this previous result here. This is 2 to the m plus 2 log 2. Okay, smaller or equal than pi of square root of x log x plus, here I write 4 this term is 4 times 2 to the m, and 2 to the m is smaller than x, so 4x log 2. Well, and finally, this must be small pi of square root of x is smaller than square root of x. So as I said, it's a little bit tricky. Now we take psi of x over x, and psi of x over x must be smaller or equal than log of x over square root of x plus 4 times log 2. And when x tends to infinity, this tends to, the right hand side tends to 4 times log 2, so in particular this term is bounded above. This expression is bounded above. Of course, this is not at all the best bound, but it doesn't matter. For our purposes, it doesn't matter. It's a very rough bound. Notice that I have bound here, for instance, in this sum, we have put directly all primes smaller than 2 to the m plus 1, while we only need some of the primes there. We have bound pi of square root of x by square root of x directly, so the bound is very, very rough, but it's enough for our purposes. Okay, so this function, in fact, this quotient is bounded. And we have more or less all the ingredients to finish the proof. Now, the rest of the ingredients are essentially of an analytic nature. So, next result, we are going to show a couple of results, or to at least to exhibit or to give a rough idea of the proof of a couple of results of analytic nature that are the following. First of all, would be a proposition related with Laplace transforms. So assume that you have a piecewise continuous function from 0 to infinity. Assume it is piecewise continuous. Piecewise continuous and bounded. Let us consider the following function, the integral g of z equal to the integral from 0 to infinity so the Laplace transform essentially. Okay? This integral defines a holomorphic function on the right half plane of positive number. Okay, this integral always defines a function here. So assume that this function could be analytically continued. We have this function defined here, but assume that this function could be analytically continued to a larger open set that includes all the imaginary x's. Assume that it happens, that this function could be analytically continued to some larger open sets. What is important, this open set must include the imaginary axis. So, and let us denote this analytic continuation, let us still denote it by big G, of course. So, in this case, this integral is convergent. And in fact, the value of this integral would be g of 0. So it's quite natural, well, in fact it's quite natural. With z tends to 0, naturally you would assume that the value of g at 0 would be taken when z tends equal to 0 here. So, but it's necessary to show that in fact this integral exists in this case. Okay, this is a theorem related with a result related with, let's say, with a Laplace transform. And, okay, let us give an idea of the proof of this result, at least. It's a little bit technical, but let's give an idea. So, To give a proof, let us consider the following function. Take some lambda positive, and let us consider the function g of lambda z equal, g lambda z equal to the integral from 0 to lambda, of ft. So it is in a bounded domain, in a bounded closed interval. So g lambda z is an entire function. It's an entire function, okay? Okay, the objective will be to show that this entire function, when you take the value 0 in this entire function, yes, in this, this is respect to t of course, when you take the value 0, here you can replace z by 0 without any problem, g lambda of 0 tends to g of 0, when lambda tends to infinity, will be the objective, where g, remind that it's not, g of 0 is not defined like this. G is the analytic continuation of the function g. That is not exactly defined with this integral, okay? So for that, we are going to consider the following path. Take some r bigger than 0 and take here a half circle. Recall that your function g can be analytically extended here to some neighborhood, so it can be analytically extended slightly. So we can continue a little bit here, and to close here. We're going to consider this path to continue a little bit. We can always, given some r, given a fixed r, we can, of course, this distance here we could call delta of r. This distance here is not the same for every r. I mean, the analytic continuation could be in an open set that could be something like this. Imagine that could be narrowing. So if you have an open set on the right part of this line, when you take some big r, perhaps your delta r you have to take here is very, very small, perhaps. Okay? But anyway, you can take some delta r strictly greater than 0. Okay? And let us consider the following integral. Let us consider the value g of 0 minus g lambda of 0. And we're going to write this value in the following tricky way. This is one of the, there are a lot of tricks in this proof. Call gamma of r this path here, oriented directly, oriented counterclockwise. So this would be 1 over 2 pi I times integral of the function g of z minus g lambda of z times, I'm going to erase this beautiful drawing, and instead of writing the usual Cauchy integral, the trick is to write the following e lambda z 1 over z plus z over r squared. This is a quite tricky integral. Let us observe that this integral, using residue theorem, which is the value of this integral, you have to take the residues at the poles of the function in the integrand. This function in the integrand only has a pole when z is equal to 0 inside this contour. So it has a pole here. And the value at that pole, you multiply this by z and take the limit when z tends to 0, you would have, you multiply this, the integrand by z, so when z tends to 0, this term is going to disappear, this term here is going to tend to 1, and you have here g0 minus g lambda of 0, what we have here. So this equality is true by residue theorem. Okay? This equality is true by residue theorem. Let us also observe that when z is equal to r, this term 1 over z plus z over r squared can be written like this as z plus z bar times r squared, and this is 2 times the real part of z over r squared when you are on this half cycle, a slightly bigger half cycle. Okay? And so the idea is to bound separately, to bound this integral. We are going to split the integral in several integrals. For instance, the first integral we are going to consider is this part here. So the integral about integral along gamma r plus. We are going to denote gamma r plus the right hand side of this path. So we are going to consider this integral, the expression over this path. And so you can bound this integral. So how can you bound this integral? Okay, so first of all, we are going to bound the integrand. So g of z minus g lambda of z. If you are on the right half plane, g of z is defined by that integral there. G lambda of z is defined by this integral there. So this would be the integral from lambda to infinity of f of t okay, and this can be bound because we are assuming that the function small f is bounded, and this integral also can be bound, so this is over real of z. Okay, you only take the absolute the modulus of this expression. It would be e minus t real part of z, and you integrate directly. Okay, so you have that. So this integral here would be smaller than all this integrand. Here would be smaller than this part, m e minus lambda real of z here, times e lambda real of z, and times this expression is this one, 2 times real of z over r squared. And after that, you have to bound this. You divide by 1 over 2 pi here, and you multiply by the length of the path which is pi r. Okay, so well, this vanishes with this vanishes with this, pi vanishes with pi, 2 vanishes with 2, r vanishes with r, so you have m over r, I think, yes. So the first integral, let's say this first integral is E1 is bounded by m over r. Second integral, okay. For the second integral, for the negative part, we're going to separate the integral of g lambda of g and the integral of g lambda. We're going to separate in the terms on this side. For g lambda is easier because let us consider the integral of g lambda, call it I2, the integral of g lambda. So call I2 the integral of over the negative part of the path of g lambda. z. Dun, dun. Recall that this function g lambda is entire now, and you are integrating by a path here. But this is an entire function, so you can change your path, in fact, by any path, any other path that goes from this point to this point here. So we could change the path by this path, this half cycle here. So you can replace the path by this half cycle. This gamma r minus is going to be this half cycle. And here you can bound without many problems. So this term here, g lambda of z, e lambda z, can be bound. Why? G lambda of z can be bound by something as e lambda real part of z times m, a bound of f, times this integral of e from 0 to lambda here, so this integrand, and this would be something as you work a little bit, you obtain that this is smaller or equal than m over the real part of z. You can have to take the absolute value of the real part, because now you are in the negative part of the numbers with negative real values, negative real parts. Okay. So finally, this integral y2 over r is smaller than 1 over 2 pi. This integral here, 1 over 2 pi a, I forgot. Write it here. This term here would be m over the real part of z. This term here, as we are on this half circle, we can apply the bound over there, so it's 2 times the real part of z over r square. And finally we have pi r, the length of the path. And I think it's enough, so this goes with this goes with this, pi, and you obtain again m over r. Again, m over r. Okay, the hard part is to bound the rest, let's say, to bound this integral for g. Why it's harder? Because you don't know an expression for g. You know that g admits analytical continuation, but you don't know, in fact, an expression for g. So the trick, essentially, to bound to obtain a bound of this expression the trick could be, well, first of all, the path is something like this. Okay, the path is something like this. So first of all, the idea is to take some, this length is delta r, take some delta 1 here, and to consider, to split again your path in 2 parts. First of all, to consider the path here, only up to some delta 1. And, well, working a little bit, you obtain that this integral here can be bound, let's call it I3, this integral can be bound by some 1 over 2 pi, some constant m, let's call C of r, that could be a bound of, this could be a bound of the function g that you don't know over this path, an amount that could depend on some on r, okay, times something like 1 over delta r plus 1 over r pi r and e to the minus lambda delta 1. Okay, delta 1 in principle you have chosen any delta 1 like this. The idea is that once you have fixed in this expression, when you have fixed, for instance, let's say r and delta 1, this expression tends to 0 when lambda tends to infinity. Once you have fixed r and delta 1, okay? So after that, you will have to make a choice of delta 1. And finally, you have to bound in these small pieces here. To bound the integral in these small pieces here. This is also a little bit, well, you have to make some computation. Let's call I4 this integral. And, well, also after making some computation, you obtain that this integral is smaller than 1 over 2 pi c of r, the r before, times 2 times r sinus, that comes from some angle you have to find here. It depends on the delta 1 you have found here, of delta 1 over r. Okay, now you have to sum all these 4 integrals, I1, I2, I3, and I4. So, first of all, if you take some positive epsilon, it's easy to choose some enough big r such that this is smaller than epsilon over 4, okay? The second integral that I don't remember where it was, it's also smaller than epsilon over 4, okay? Once you have chosen this big r, here you can choose, you already have fixed your r. So here you can choose delta 1 such that this expression is small enough. Also, it's smaller than epsilon over 4. You have fixed r. And now, as you have chosen r, you have fixed r and delta 1, you can, in this expression, choose some lambda such that this expression is smaller than epsilon over 4. Finally, so it's quite tricky. But finally you obtain that the difference g lambda 0, g0 minus g lambda 0 is smaller than epsilon for some lambda big enough. Okay? So it's a little bit complicated, but okay. So, second, there is a second analytic tool that I think I will only give the statement. I will only give the statement because also the proof is, well, not terribly complicated, but more or less in this, has some similar ideas. There's a second analytic tool that is the following. Assume that now you have a second result. Assume that you have a function, a positive function like this, piecewise continuous, and increasing, or non-decreasing, at least non-decreasing, okay? Such that the function is big O of x, so the function divided by x is bounded at infinity. Then, if you consider this function g of z, the function z times 1 to infinity of f of x, 1 over x to the z plus 1, d of x. Consider this function here. So this function defines a holomorphic function on the right, on the plane real part of z greater than 1. This is quite easy only from this assumption here. This defines a holomorphic function here. And if it turns out that this function verifies that if there exists some real number c, in fact, some positive real number, such that the function g minus c over z minus 1 can be continued to a neighborhood of this line, can be continued to a neighborhood of real of z equal to 1, then limit of f of x over x it is equal to C. This function can be continued in this way. So, assume we have proven this theorem. If we have proven this theorem, we could apply this theorem to the function psi of x. Consider the function psi of x. Consider the function psi of x. So the function psi of x verifies that it's piecewise continuous and it's non-decreasing. And the last lemma we had proven said that psi of x over x was bounded above. So psi of x is a big O of x. So we are in the conditions of the statement here. So we consider this function. Consider this function, and well, this is a function defined in where the real part is greater than 1, and the statement says that if there is some c such that this can be continued, we have that. But okay, but there is such c. Why there is such c? Because remember that in another previous lemma we had shown that this was equal to z, sorry, minus zeta prime of z over zeta of z, okay? And we know that zeta of z has no zeros on the on this line. So this denominator is different from 0. 1 over zeta of z can be well defined. So this function here can be extended to some neighborhood of this line real of z equal to 1, okay? So we are in those conditions. And if this happens, why this happens? Okay, this function here has a pole at z equal to 1. In fact, it has a pole at z equal to 1. And why it has a pole at z equal to 1? Sorry. Yes. Let me see, yes. It is correct. I'm sorry, let me... Okay, the fact is that minus plus 1 over z minus 1, this term, okay, z is not, okay, of course, z is not, yes, the zeta function is not defined at this point, the point 1. But this logarithmic, because it has a pole of order 1, okay, so this term, this logarithmic derivative at this pole, in fact, zeta of z, zeta prime of z, as it has a pole here, is the only point where perhaps it could not be correctly defined, but it has some expansion as minus 1, with minus 1 plus, etc. Always this, when there is a pole of order 1, the expansion of the logarithmic derivative around this pole is always of this type. So we have now, no, plus here, I think it's, I don't, sorry, I always have mistakes with this, yes, I think it's like this, okay, it's like this, okay, so, anyway, yes, it must be like this, so in this sense, this term here, this function here can be extended to some neighborhood, because this is that, plus something that is holomorphic, in fact something that is can be extended because of the non-vanishing of the zeta function on this line can be extended to a neighborhood of this line, so this function can be extended to a neighborhood of this line, so we are in the conditions of this theorem So we can deduce that the limit of psi of x over x must be this number here, this number 1 here. And this was the equivalent condition to the prime number theorem. So it is quite involved, in fact, the proof. For the proof of this theorem is not really complicated, but essentially it uses the previous one. So essentially it uses that you can replace x by e to the t, I guess, something like this, so e to the minus t in this. Yes, you have to replace x by e to the minus t, I think, something like this. Plus or minus t, I don't remember exactly. And, well, to work a little bit to have an integral as before and to apply previous results. As the conditions of the functions here are enough to guarantee that you have all the conditions of the previous result, and using this result you can obtain, it's not at all immediate. Of course, there are many computations to do, but I only wanted to say that, well, using these tools that are not really complicated, complex analysis, but they are long, of course. I would need many lectures to give all the details here, but I don't want to extend it. So, but using the results, a proof of some, let's say, number that some result that comes from the theory of numbers can be obtained using only analytic tools. In fact, I think there is some proof of the prime number theorem which does not use complex analysis tools. There is a proof of Erdos, but I have never read to that proof, so it must be more complicated, perhaps. But I think it's more or less the ideas of the simple and the simplest proof, and it is somewhat hidden, the fact that the key point is that the zeta function does not vanish on this street, and this is somewhat hidden here. And this is true, that is the key fact that this function does not vanish there. So, okay, it would be an application of some of the results of complex analysis to provide at least an idea of the proof of a deep result in this case, which is a prime number theorem. And I stop here.